YouTube. All right, so this class is about differential topology. So before telling you about the administrative things, let me just kind of say what the course is going to be about. So it's going to be about topology. So what is topology? Topology is the study of spaces. So we're going to study spaces, more specifically manifolds. But from a differential point of view. So differential, or some people, differentiable, it means that we want some kind of derivative. So we want a derivative, so a smooth structure. And this is where sort of the tangent space is going to come. So just to give you a slight historical perspective on this course, it's a course that's been taught at INPA for a long time. And for a long time, it was the first time people saw what a differentiable manifold was. And that's no longer the case. So now we have a course on differentiable manifolds that's called Analysis on Manifolds. So this course will no longer, we won't really talk about manifolds in a lot of depth. But today I'm going to do a recall, sort of an introduction and review some things about manifolds. But before that, let me just say that this course, after we review manifolds, which we'll finish today, what this course is really about is about studying manifolds from a differentiable point of view. So not just studying what they are, but studying some other things. So I would say the course has, there are two elements that we're going to see in the course. And one is construction. So construction of, like building new manifolds. And here, basically, there are two subtopics. One is transversality, and the other is Morse theory. So in the transversality theory, we will see a way to, first of all, build many manifolds using the inverse or the implicit function theorem, and how to perturb manifolds and how to embed manifolds into a big Euclidean space. And then towards the end of the course, we're going to talk about Morse theory, which is a very beautiful theory of how to build manifolds from little pieces. So how to glue little pieces together to build a big manifold. And in the meantime, there are some things that are pretty technical about CK topology that people might be interested in, and density and stuff. And maybe some people in dynamical systems have a particular interest in that. But that's going to be here. And then after that, I would say there is a little bit of classification or invariance. And this is really some flavor that geometers and topologists are very interested in general, which is how to differentiate manifolds, or how to differentiate spaces, how to make sure that spaces are different. And here, we have different invariants, but in this course, we're going to be interested in differential invariance. So we're going to talk about degree, theory, intersection number, etc. Okay, so we're going to see that if you want to classify maps, there's something called the degree in certain cases, and that will be the same when the maps are homotopic. And then we're going to have some interesting converse questions, like if we have two maps of the same degree, are the maps homotopic? And it's going to depend on the situation a little bit. And we're going to have some beautiful theorems about that. And intersection in general, like two submanifolds intersecting. Sometimes we have intersection numbers. Other times we have more complicated things. So there are additional topics here that I want to cover too, which one of them, which I find really beautiful, is the Pontryagin-Thom construction, which is basically a generalization of the Thom theory the Thom theorem that comes up in the more classical theory of degrees and intersections. So I think this course will be a little bit longer than the historical differential topology class, especially because I'm going to go very quickly over the definition of manifolds. But it is probably going to be very similar to the course I taught last summer, which was online. So let me just kind of do an outline of the course. So an outline of what we're going to cover is, so basically today, we're going to do a review of smooth manifolds. Then, starting next week, we're going to talk about the transversality theory. So that's going to be probably the most technical part of the course, which will use some tools from functional analysis. And then we're going to talk about degree or index theory. No. Intersection and index theory. And then we'll talk about Morse theory. And then if there's time at the end, we'll talk about some additional topics. I think there will be time. Additional topics, such as some consequences of Morse theory, which I think are very beautiful, like classification of surfaces, so 2, 3, and 4 manifolds. And don't worry, we're not going to classify 3 and 4 manifolds, but we wish we could, but we'll just say a lot of interesting things about how to build them. So a little bit of low-dimensional topology. Okay? So that's the outline of the course. As I said, it's going to be pretty similar to the course that I taught last summer online. So if you get bored and it's going too slowly, you can watch the videos from last summer. But let me just tell you what the bibliography. So I think that the most standard books for this course are these 2 books that I have here. So this is Guillemin Pollack. This is the more elementary one. Guillemin Pollack. It's just called Differential Topology. And I should say this book is very good if you've never seen, if you're not very strong on functional analysis and you just want to get to the beautiful theory, and especially the number 2. It's very good about in this part. I mean, it does transversality too, but in a kind of weaker sense than we will see. But I strongly recommend this book it's a pleasure to read. It's a very nice read, for the weekend, the late nights or something. It's very beautiful. And then on the other hand, there's this other book by Hirsch, which it's called Differential Topology as well. And this book is kind of the opposite. Or it's a lot more technical. It's very dense, and it's kind of harder to read. But it has a lot of stuff. So I think it's a very good reference. If you start to read from the beginning to end, it's going to be a slow process. But I think you should try to do that too this summer. You should try to read this book, not necessarily the whole book, but most of it. And this book will have the material on almost everything. But it's written in kind of a heavy way, so I'm just warning you. And then there's another book, which I quite like, and I'm going to use quite a bit. It's a bit more abstract than Hirsch, but it's actually a little simpler. It's Golubitsky, Guillemin, and it's actually about a slightly different subject. It's called stable mappings and their singularities. And about the second half of the book is not relevant for this course, but about the first half has a very nice, more abstract approach to the transversality theory. So this book really is only covers the transversality part using jets and a little bit of a more modern view. The Hirsch's book is very much like you go into the charts and it's kind of heavy. And this book, I think, is a little more big picture. And I'm actually going to follow, for the transversality part, I'm going to follow this book a little more, a little closer. Okay, but I'm not really going to follow any book from beginning to end. And for Morse theory especially, I'm going to say a bunch of things that are not in any of these books. A collection of things that, I've learned in other books. I mean, I can write other references later if people are interested. But, I mean, there's always kind of a book that I like a lot. It's more of an algebraic geometry, an algebraic topology book, but there are some things that are relevant in there, which is the book by Bredon. It's called Geometry. What is it? Geometry and Topology, I think. I believe that's the title. I can't remember, but it's the main book by Bredon that everybody knows about. In this book, like I said, it has a lot of stuff that's beyond the course of this, beyond the scope of this course. That's included more in the course that is taught in the next semester, which is Topology of Manifolds. But it's still, I think, a very good reference to keep in mind. Okay, so that's the outline, the bibliography. And the last thing I want to say before we start the course is about the grading, the grades. So the grades, well, maybe I don't have to write this down. So as far as the grades, well, as you know, only the INPA students are present here today. So for the INPA students, basically, it's going to be a normal course. We're going to have problem sets every week. And there will be a final exam at the end of the summer, a written exam. And you will be graded normally as you would in any semester. I haven't decided exactly the percentages, but that's not very relevant. You should do the problem sets every week. And there will be a monitoria, but that's going to be online. Okay, but the monitor, the teaching assistant, will grade the problem sets, and he will also be there to answer questions. For the students who are not here, so people watching us online, I won't give grades, so it will be like pass or fail. So you're still welcome to do the problem sets and submit them. And if you'd like to have a grade like an ABC, I'm going to propose that you come here to Rio de Janeiro, to INPA, and take the exam on the last day. So we're going to have to see how many people are interested in doing that. So if you are online and you would like to have a grade, like not a pass, not a P or F, but if you like to have an ABC grade, I would like to ask you to send me an email to say that you're interested, and then that you would have to come here to take the final exam. I don't want to do online final exams. So I will only do online final exams if everything closes down. So if we have to all go online. But if some people are here presentially and you want a grade, you have to come and take the exam here. And we can talk to INPA to see if you can come. I think if it's a small enough number of people, you'll be able to come take the test. Okay, so you can send me an email if you're interested in that. And let me just write it down. You can find it online, but it's vgbramos@inpa.pr. Oh, and one more thing. If you enrolled in the course, you probably got an email last night that I sent about the Google Classroom. So there is a Google Classroom, which is, I'll probably be posting the problem sets on that, on the Google Classroom. So there is a Google Classroom. If you haven't received the link, I don't know what the link is off the top of my head, but if you haven't received the link, please send me an email, and I'll send you the link, and you can sign up on Google Classroom and get all the announcements of everything. I'm going to stop sending emails, so I'm going to put everything on the Google Classroom. Okay? Any questions? Any comments? Dá para ver se tem algum comentário no YouTube? Ou Não, né? Marcelo, você pode ver se tem algum comentário no YouTube, por favor? Yeah, if you're on YouTube and you have any questions or comments, please post your comments right now. I'm not going to be checking them throughout the lecture, but maybe at the end or something. Oh, and in the meantime, as far as the monitoria, so the TA, I'll let you know on Google Classroom, but it will be online. And the TA will get in touch and will say when the time is and when it's going to be on Google Meet. Okay. So, yeah. Never mind. You can't post comments online. So, sorry, if you're on YouTube, there's no way to communicate with me right now. But you can send me an email later or, yeah. All right. So let's start the class. Alguma pergunta? Any questions here? No. Okay, so let's start with a review of differentiable manifolds. So I assume that everybody is familiar with manifolds, that you've learned manifolds in a way or another. Maybe some of you learn manifolds that are just embedded into Rn or something. So I'm going to kind of do a quick review so we're all on the same page. But I'm not going to prove everything. So review of differentiable manifolds. So I'm going to start very basic. So a topological space, just so we're on the same page, topological space is a pair xt where T is a subset of the set of parts. So it's a set and a set of subsets of X, which are called the open sets, which satisfy the following properties. So such that, well, the empty set and the total space are elements of the topology. If we have a collection of sets in T, then their union is also in T. And if you have a finite number of sets, then their intersection is also in T. So if you fix a topology on a set X, then the sets, the elements of T are called open sets. So fixing T, fixing X and T, the elements of T are called open sets of X. Okay, so of course, for the same X, you can choose different topologies. I think everybody has seen that before. Okay, and usually when T is understood, we'll just say that X is the topological space with the topology implicit. Okay, any questions? Okay, so a base, or a subset B of the topology is called a base if for every element of T, you can write V as a union if for every V there exists a collection of B such that V is the union of U alpha. Okay, so an example of a base. So here, a simple example is if you take Rn with a standard topology, so everybody knows what the open sets are in Rn, and you can consider the base, which is the set of balls of all the possible radii with all the possible centers. So where x is a point in Rn and R is a positive number. Okay? All right. So now we can say that a topological space and from now on I'm going to drop the topology from the notation. So a topological space X is second countable if it admits, when I say it, again, I mean the space with the topology that's implicit. Okay, so if it admits a countable base. Okay, so of course the topology in general is going to be uncountable, but if we can find a countable base, then we'll say the space, the topological space is second countable. Okay, and an example, again, is Rn with the standard topology. Of course, this subset here is extremely uncountable. It's not uncountable. It's not countable. But it's not very hard to think about another base which is countable. So if you take Rn with the standard topology, you can consider a base which is very similar, but now you only take the points with rational coordinates and the radii which are rational numbers. So now you consider the base B tilde, which is the set of balls such that x is in Q to the n, and R is a rational number which is greater than 0. Okay, so this Rn with a standard topology is second countable. So this, so Rn is second countable with a standard topology. Okay. All right. Any questions? I'm going kind of quickly because this is probably stuff that you've seen before, but if you haven't and you're here, you can stop me. If you're not here, if you're on YouTube, then you can write down your question. You can ask me. Maybe at the end I can connect on the Google Meet this afternoon, and I can answer some questions. Okay. So another definition. It's kind of technical to start, but I want to give a definition where you understand all the words. So a topological space is Hausdorff. If for each pair P and Q in X with P different from Q, there exists two open sets, U1 and U2 open sets, such that P belongs to U1, Q belongs to U2, and U1 doesn't intersect U2. So if you can separate any 2 points with open sets. So if you have a point P and a point Q, you can find two open sets around P and Q which don't intersect. That's what it means to be Hausdorff. Okay, this is not a general topology class. I'm not going to be giving you tons of examples. You can see that in another book. But there are lots of examples of things that are not Hausdorff. But most things that are not too pathological will be Hausdorff. So Rn, for example, is Hausdorff. Again, Rn with a standard topology is Hausdorff. I can say this is a very easy exercise. Okay. And one more definition. Sorry for a bunch of definitions in a row. But one more definition is two topological spaces x1 and x2 are homeomorphic if there exist continuous functions f from x1 to x2 and g from x2 to x1 such that g composed with f is equal to the identity on x, and f composed with g is x1, and x composed with g is the identity on x2. Okay. And I should say I didn't quite define what continuous means, but I'm kind of giving you some basic definitions and skipping some other ones. But continuous, I think everybody probably knows that it just means that the pre-image of an open set of this one is an open set of this one. So all the sets are endowed with topologies, and it has these properties. Okay? All right. So I think this is also pretty straightforward. And now I can actually make the definition of what a topological manifold is. So a topological manifold is a topological space, is a second countable Hausdorff topological space such that every point P, or every point is contained in an open set which is homeomorphic to an open set in Rn. Okay, so it means that, so I have this topological space that could in principle be kind of complicated, but so every point in the topological space has an open set which is homeomorphic to an open set in Rn. Okay? And we're going to assume that the n is the same for the whole space. So you can prove that it's actually not so obvious, but you can prove that in each connected component, the n cannot vary. But I'm just not going to even prove that. I'm just going to assume that it's the same n for every point. Okay, so we assume that the n is chosen, that n does not depend on P. Okay, again, if you don't assume that, you can prove that for each connected component, the n is the same, but then you could actually have different connected components of different dimensions. We don't want to do that. And very often, we'll say that, we'll assume that the manifold is connected. Otherwise, we say it's several manifolds. So there's two manifolds. But, depends exactly on the theorem. So I won't promise that I will always assume it's connected. OK. So any questions about this? All right, so now let's talk about what it means for a manifold to be smooth. So far, I haven't mentioned the derivative at all. So this is what's called a topological manifold. So now let's see what a smooth manifold is. So in order to do that, let me make a couple of definitions. So let X be a topological manifold. So a chart is a homeomorphism from an open set of X into an open set of Rn. So we know around each point there exists a chart by the definition of a topological manifold. So that's what a chart is. And an atlas is a collection of charts that covers the whole manifold. So it's a set of charts. An atlas is a set of charts. So I'm going to call this A. Phi that goes from Ui into Vi. No, alpha, which are indexed by some set such that the union of all the U alphas is equal to the whole topological manifold. Okay, so we just, if you have your topological manifold, a chart is a homeomorphism to something in Rn, and an atlas is just a covering with charts. Okay, so each point, the definition is right here. Okay, and an atlas is called, All right, so now we say that an atlas is CK. So a CK atlas is an atlas such that, so what happens is now if you have an atlas, if you have two charts, and if their domains coincide, then you can talk about the transition function that goes from Rn to Rn. So let me draw the picture here. So here's your manifold, your topological manifold. And then say you have two charts that coincide. So we have a pink, a green, and a pink. So this one takes values in Rn. This one takes values in Rn. And at the intersection, you can look at the image over here, and you can look at the image over here. So I guess you can go like this, and you can go like this. But now you can see that you can compose, this is a homeomorphism, so you can compose this map with this map, and then you get a map from here to here, which is a homeomorphism of two open sets of Rn. So this is a homeomorphism of two open sets of Rn. So you say that these two charts are CK compatible if this homeomorphism happens to be a CK map. So all the first K derivatives are continuous. Okay, and the whole atlas is CK if all the charts in this atlas are CK compatible. So let me write down what this means. It means that it satisfies the following property. So if U alpha intersects U beta, then you have the map phi alpha inverse composed with phi beta that goes from phi alpha of U alpha intersected with U beta into phi beta of U alpha intersected with U beta. If this map is CK. Okay, so here is the map phi alpha, here's the map phi beta. So I want to apply phi alpha to the intersection of the two domains and say that this map that goes from here to here to here is actually a CK map. Okay, and this is for any k from on, and it could be infinite. Okay? So now, I say an atlas, a CK atlas is maximal if it's the largest possible CK atlas. So if there's no other CK atlas that's bigger than it. So a CK atlas A is maximal if, so if you have another CK atlas which contains A, then it has to be equal to A. So in any other words, if you can find another chart which is CK compatible with all the other charts in the atlas, then it has to already be in the atlas. Okay? So this is kind of a technical definition, but it's just to say that you use the word maximum to just say that all the possible charts that are compatible are already in the atlas. And then finally, you can define so a CK differentiable or differential structure on X is a choice of maximal CK atlas. Okay, so you choose one of them. And that's what's called a differential structure. Okay? So an observation is that if you just fix one CK atlas, then it's always contained in a maximal CK atlas. So any CK atlas is contained in a unique maximal CK atlas. So really, this is kind of a very subtle technicality. So all you need to define a CK structure is to pick one CK atlas. So you need to cover the whole manifold with charts such that they're all CK compatible. And once you do that, then the differential structures is the collection of all the possible charts that are CK compatible with the charts that you chose. Okay? So anyway, this is kind of technical, but so you say that a CK, I guess, sixth definition. So a CK manifold is a pair XA where X is a topological manifold and A is a CK differential structure. Okay? So let's talk about some examples, because I think it's kind of very abstract. Let's talk about some examples before we continue the theory. So the first example is Rn. Again, Rn is an example for almost anything. So if you take Rn, it's kind of obvious that it's a topological manifold. I mean, it is obvious that it's a topological manifold because you can just take, for any point, it's contained in an open set, and you take the identity, and that's a homeomorphism into an open set of Rn. But it's basically not hard to see that it also admits the structure of a CK manifold. Okay, so I guess just the inclusion, so basically you just look at CK maps. It's kind of tautological. It's hard to write down, but Rn is naturally a CK manifold. Okay. Whether it's possible to change the CK differentiable structure to not the canonical one, but another one, it's a much more subtle question, and it's possible in higher dimensions. But it's very technical. So basically, if you take a homeomorphism for every open set into something else where this homeomorphism is not smooth anymore. But these other charts, when you look at the transition functions, these are all smooth. That's possible, but it's very subtle, so I'm not going to talk about that right now. It's a little too advanced for this course. But another example that is very interesting is Sn. So that's the n-dimensional sphere. So that's kind of the next example of manifold. I guess you can talk about curves and surfaces, but I'm going to skip those kind of easy examples. And let's just talk about the spheres in higher dimensions. So this is just the set of points in Rn plus 1 such that the norm of x is equal to 1. And how do you know that this is a manifold, for example? So it's not completely obvious. I mean, if you have seen manifolds before, you probably know how to do this. But I guess the simplest way is to look at the stereographic projection. So this is a CK manifold for every k. But kind of one way to see this is by just looking at the stereographic projection. So given a sphere, you can find two charts, which basically is the stereographic projection with respect to the North Pole. So this is a homeomorphism. So I guess you have phi1 or phi-n, which is the stereographic projection from the North Pole. So this is a homeomorphism of the sphere minus the North Pole. And then you have another one, which is the stereographic projection from the South Pole. So this is a homeomorphism of the punctured sphere into Rn. And when you look at the intersection, so everything except the two poles, it's not hard to see that this is actually going to be a diffeomorphism, a smooth infinity diffeomorphism from Rn to Rn. So you can do the calculation if you want. Okay, I'm going to spare you from that, but this is in any kind of basic manifolds textbook. Okay, so it's not hard to see that these maps are C infinity compatible, and therefore C k compatible for any k. And what this example shows you is some phenomenon that's very interesting that's happening here, which is we're defining a manifold by saying, some function, by looking at the level curve or the level surface of a smooth function. This is actually a more general phenomenon. So this is kind of an example that you can look in much higher generality. So I guess you can say number 3, which is if you take a function from Rn to R, which is Ck, and you take a point P or sorry, a value A in R, which is a regular value. Being a regular value, if you don't remember what it means from analysis, it just means that for every point in the pre-image of A, when you look at the differential map that goes from Rn to R, this is surjective. I guess it's the same as saying that it's non-zero. Okay? So if you have a regular value, then the pre-image of A is naturally a CK manifold. And this is a consequence of the implicit function theorem. So this is a straightforward, it's almost basically equivalent to the statement of the implicit function theorem. So this is by the implicit function theorem. Oh, I should say it's a CK manifold of dimension n minus 1. So the implicit function theorem will tell you that near each pre-image of A, you're going to have a little open set such that you're on the pre-image of A if and only if sort of it's mapped to an open set of Rn minus 1. Okay, this is almost the statement of the implicit function theorem. Okay, which I won't rewrite, but it's analysis on Rn. Okay, any questions about this? Am I going too fast? Too slow? Okay. So yeah. So now you might wonder, are there manifolds that are CK but are not CK plus 1? What's the subtlety of all the different Ks? And if you liked analysis, you probably know that there are lots of maps that are C1 but not C2, or C2 that are not C3. And these questions of how many derivatives you have, it's actually pretty subtle. So what I'm about to tell you is that it actually doesn't make a big difference from the for studying manifolds, if they're C1, C2, or C infinity. So basically, the only difference is between C0 and C1. But once you know something is C1, up to an easy transformation, it can just basically think that it's a smooth manifold. So let me just write that more precisely. And I won't prove all these details, but I just kind of want to state it once. So let me say, let me define what a CK map is. It's pretty straightforward, but if M and N are CK manifolds, a map from M to N is CL, where L is at most K, if for every point, every P in M, there exists a chart around P and a chart around the image such that when you apply the transition function, the map is CL. Okay, so there exist charts around P into V over N, and a chart U tilde based out of N containing the image F of P into V tilde in Rn. Actually, let me draw the picture before finishing. So you have your manifold M, you have your manifold N, and you have a map So what does it mean for a map to be CL? It means that you can choose, for every point P, you can choose a chart phi here, and you can choose a chart psi here into the image, such that when you look at the transition, this map is CL. So, such that there exists a chart, and we can assume that U is sufficiently small so that phi of U is contained in U tilde. Well, let me just write this. Such that psi composed with phi composed with F composed with phi inverse is CL. And here I'm choosing, U sufficiently small so that the image of U is contained in U tilde. Okay. All right, so it's exactly what this picture is showing. Okay? Yeah. And I should say that to be able to do that, you assume that the map is continuous to begin with. Okay, so you start with a continuous map, and you say that if it's continuous, then you can say that it's CL if it satisfies this. And it only makes sense to talk about this if L is less than or equal to K. Why? Okay, here's a question for you. See if you're paying attention. Why do I have to assume that L is less than or equal to K? Anyone? Because, I have a map from Rn to Rn, or Rn to Rm, actually. They don't have to have even the same dimension. Why do I have to assume that the L is less than or equal to K? Well, I have to assume L is less than or equal to K, just to make sure that this is well defined. Because I'm just saying pick one chart, and it's CL. But if I pick another chart, then I have a transition map. And I know that this transition map is CK, but I don't know if it's CK plus 1. I only know that it's CK. So if L was bigger than K, the new transition map, after I change the chart, will be the composition of the transition map with this map here. So to make sure that the composition is still CL, I will need to use that the transition map here is CK for a K bigger than or equal to L. Otherwise, I won't conclude that the composition is CL. Okay, so this is a little point, but please take notice. Any questions? Is this clear? Please ask now. Yeah, fala. Sim. Is it okay if I speak in English? Yeah. So what I'm saying is, so what is this map? This map is basically the original map F, but looked in from Rn to Rn. So after you choose a chart around the base point, around a point that you're choosing and a point in the image, then you can see this map as a map of subsets of Rn. So then you can talk about what it means to be CK, CL, C infinity, any C that you want. Okay? But this is just choosing one chart. If I choose another chart, then the map in these other coordinates is going to be the composition of the transition map with this map here. So if I'm assuming that this map is CL, I'd like to conclude that this other map here is CL as well. But I know the transition maps are CK. So I can only conclude that this thing is CL still if this K here is bigger than or equal to the CL. You see? So that's why, you assume. I mean, you could, if you really want to brute force the definition, you could define this for any L and say that this is CL for every possible chart. But that would be a really strong definition. And I think it would be actually very hard to find CL maps. So the natural thing is when you have a CK manifold, you define maps that are either CK or CL for L less than K. Okay, so that's that. And then now, you can also, in particular, you can talk about diffeomorphisms. So if you have two CK manifolds, so two CK manifolds. So sorry, did you understand now? Okay. Two CK manifolds M and N are CL diffeomorphic again for L less than or equal to K if there exist CL maps M, F from M to N, and G from N to M, such that G composed with F is the identity on M, and F composed to G is the identity on N. So with these definitions, I can tell you about a very nice theorem, which will basically say that it doesn't really matter which K you pick. So the theorem says the following. So let fix a K between 0 and infinity. Then every CK manifold is CK diffeomorphic to a C infinity manifold. So what does that mean exactly? So let me explain this with words. So this means the following. So say you have a manifold, a topological manifold, and a CK atlas, maximal atlas. That means there is another X tilde and another atlas, which are CK diffeomorphic to that. And this new atlas, you can throw away a bunch of charts and just keep a C infinity maximal atlas. So when you have a CK atlas, you say that this manifold is a C infinity if you can throw away some of the charts, but still have a subset, a subatlas, which is C infinity compatible. Okay, so that's what it's saying. You can almost ignore this diffeomorphism. Just imagine, if you have a CK maximal atlas, so you basically have a bunch of charts which are all CK compatible. It is also a C infinity manifold, meaning you can throw away some of the charts, the more weird charts, and you can still end up with an atlas, so you can still cover the whole manifold in a way that the transition maps are all C infinity. So basically, yeah, CK, you have more charts because you have all these pathological maps that are CK but not C infinity. But there's nothing really in it about the manifold. It's just about the CK versus C infinity in Rn. Okay, so that's the first result. And actually, any CK map, so the second part, that is also true about maps. So 1 is this, and 2, hold on, is, okay, let's write, sorry, this is number 1. Number 2 is let 1, no, let's just write it like this. If two C infinity manifolds are CK diffeomorphic, then they are also C-infinity theoremorphic. They are also C-infinity diffeomorphic. Okay? So, and this is true if you take L and K in between, but I don't want to bother with so many details. But I guess the point of this theorem is that basically if K is greater than or equal to 1, you might as well assume K is infinity. So there are only really two classes of topological manifolds that you should worry about. The topological manifolds that are just C0, so they don't admit a differential structure, and the topological manifolds that do admit a differential structure. And sometimes you can classify them like you have one topological structure and you can have many smooth structures for the same topological structure. So it's very subtle, and we're not going to really talk about this classification question very much. But this theorem is just kind of an excuse, or that I define CK manifolds, but I'm only really going to care about smooth manifolds. Okay, so if you're interested in the proof of this, I'm not going to give it here. It's kind of technical and it's not very enlightening, but you can find it in Hirsch's book. So this is in chapter 2 of Hirsch. So it's a consequence of some of the more obscure transversality theorems. So if you're interested, it's in there. But the conclusion is that from now on, we're only going to do everything on smooth manifolds, so on C-infinity manifolds. So from now on, I will assume all manifolds are C-infinity. Okay? All right. Any questions about this? So now I want to talk about the tangent and the cotangent bundles. Okay, so let's talk about tangent and cotangent bundles. Okay, so now let's, sometimes I kind of tend to go back and forth between X and M as my manifold. So now I actually have switched to M. I usually like M better, but the book I'm following uses X. So I kind of go back and forth. But M and X are both manifolds. So if I write M and then I write X, so M is equal to X. Okay, so let's define the tangent space. I think you've all seen this definition before, but maybe I'll write it again. So let M be a smooth manifold. And I'm going to say one last time that smooth is the same as C-infinity. And let P be a point in M. We're going to define the tangent space as the following thing. So we define the tangent space at P to be this set of curves that go through P, quotiented by some equivalence relation. So this is the set. So this is a curve that's smooth such that gamma of 0 equals P. So the idea is how do you define, I think you've all seen this before, but let me draw the picture. Quotiented by some equivalence relation. So if P is a point on the manifold, I want to define what it means I want to define the tangent space. So how do I think of the tangent space? What's the tangent vector? It's basically the tangent to a curve that goes through P. So I think of a curve, and then I look at that derivative. But how do I really do that in a way that makes sense? So I have to look at all the curves that go through P, and I have to quotient by some equivalence relation. And the equivalence relation is the following. So gamma 1 is equivalent to gamma 2 if for any chart, or for one chart or for any chart, it doesn't matter, phi such that P is in use, or any chart around P. When you look at the chart composed with gamma 1, so gamma 1 is so here's, let me look at this. So it's pretty simple, but here's the chart, and I have a curve, a blue curve, and a green curve, and I want to say they have the same tangent vector at the point P. So how do I do that? I just have to look at the chart. So the chart will translate this to Rn, and then I have a map from R. So now I can compose these two and say that the maps have the same derivative at time 0. So if you look at d dt of this for t equals 0, this is the same as d dt for t equals 0 of the map phi composed with gamma 2. Okay? And what's interesting is that a vector, so what is a vector? A vector is an element of the tangent space. So a vector, which you can think of as an equivalence class of curves, induces a derivation on the space of smooth functions. So C infinity of M is the set of smooth functions. It's smooth maps that go from M to R. Smooth. And what is the derivation? The derivation is just the following thing. So given a vector V, let me just write it like this. The class of gamma applied to the function f, this is just d dt at t equals 0 of f composed with gamma. Okay, so when I compose, so my function goes from the manifold to R, and my curve goes from R, or from a subset of R, to M. So this is gamma. So when I compose gamma and f, I get a function from R to R. So I can look at the derivative at 0. Okay? And what is a derivation? If you haven't heard this word before, a derivation on C infinity M at, so I say that V is a derivation at P if the following properties are satisfied. If V of F plus G equals, so if V is a map that goes from C infinity of M to R, such that V is linear, so V is R linear. So this means that V of AF plus G equals AVF plus VG. for every real number. So if A is a real number, and f and g are smooth functions. And v satisfies the Leibniz rule. So v of f times g is vf g of p plus f of p vg. Okay? So what I told you there is that a vector defined this way induces a derivation. And it's an exercise to see that a derivation induces a vector. So it's an exercise to see that there's a bijection between that map is actually a bijection, the map that goes from the tangent space to the set of derivations on C infinity at P is a bijection. Okay? So a lot of times you'll see this as the definition of the tangent space because it's a little cleaner. And then you'll see that, this going from here to derivatives of curves is a bijection. But what's nice about this is that this clearly has linear structure. So it's easy to see that the set of derivations is a linear space. Okay, so it's easy to see. I mean, it's kind of obvious that, almost obvious that you can add derivations and multiply them by real numbers. Okay? So exercise 1 and exercise 2, therefore, this space has a natural linear structure. Okay? And now we can talk about, so this is a linear space for every p, and it actually has a very natural basis. So if you choose a chart, if you fix a chart, then this space inherits a basis. Okay, so let's let phi into v of Rn be a chart. So this is the end of the exercise. Be a chart around p. So I'm going to write it like this. So phi is a function from u to Rn, so I can think of it as n functions. So x1 through xn, where each xi is a function from u to r. So now phi induces a basis of the vector space TPM. And what is this basis? Well, this basis is very simple. Basically, it's the following thing. Well, you can write it as either a curve or or using derivations. But basically as a curve, so if you look at your chart, so this will take this to a open set of Rn. We can suppose that this is a little ball centered around 0. So now you can just consider the curve that just goes in one of the coordinate axes. And this, when you look at the tangent space there, the tangent vector there, that's going to be the derivative at 0. That's going to be a tangent vector in each direction. Okay, so you can define it like this. So you can define a curve gamma I, which is basically phi inverse of 0, t, 0, where this is in the ith coordinate. And then the equivalence class of this guy will be a vector. So, you can basically, you have that the equivalence class of gamma 1 all the way to gamma n, this is a basis of TPM. Okay, so this is a way to see, this is how to define this basis using curves. But if you like derivations more, maybe it's actually simpler to see this is a basis using derivations. These have nice names, and they're called DDXI. So you can define this thing called DDXI at the point P. And this is a derivation that does the following thing. So this, when you apply to a function f, what it does is it looks at f composed with phi inverse, and it takes the partial derivative with respect to xi at the point 0. So when you're assuming that the chart, I forgot to say this, but we often assume that the center of the chart is taken to 0. Okay, so in other words, if here's my point P, I have my manifold. So this derivation, ddxi at P, what it does is you look at your chart, you look at your function f, which goes to R, and you look at your chart here, phi, and here you have 0. So you precompose with phi, and you compose with f, and you just look at the partial derivative in the direction ddxi. And it's a very simple exercise to see that. I mean, it's an exercise of definitions to make sure you understand the equivalence between equivalence classes of curves and derivations. To see that what I define here, this gamma I, well, let me say this exercise, that this gamma I here is the same as this derivation. Or that the bijection here takes the equivalence class of gamma I to this derivation ddxi. Okay, any questions about this? Maybe this is a little abstract. If you've never seen this before, this is a little too fast. But if you've seen this before, then it maybe makes sense. Or maybe it's too slow. Okay, any questions, please? Now is a good time to ask if you're confused. No? Okay, so now we can define the tangent bundle, which is basically the union of all the tangent spaces. So now we can define what's called Tm, which is, I'm going to take the disjoint union of all these TPMs for P in M. Okay, so this is just a set for now. And I have to topologize it to introduce the topology here. And what's very nice is that this basis actually works not only at the point P, but it works in the whole chart. So what you can see is and sorry, I forgot to say that. Using this basis, we get obviously a bijection between this and the linear space Rn. And I guess maybe it's easier to see the bijection the other way around, which is before we do this, you just take, so say you take A1 through AN to the sum of AI ddxip in TPM. Okay, and this thing being a basis is the same thing as saying that this is a bijection of linear spaces. It's an isomorphism. Okay, but what is very nice is that you can do this varying P. So if you fix a chart, phi, that goes from U to Rn, or to V in Rn, we have a bijection which goes from U times Rn into the disjoint union of TPM for P in U. So this is a subset of Tm, which will take, say, a point Q in A1 through AN into the sum of AI ddxi at the point Q. Maybe I should say that to be a little more general, I'm going to say this is at phi of P. Because this way I don't really need to be fixed at 0. I can use the same chart for all the points in the domain of the chart. Okay, so this is kind of, it's very simple, but maybe if you've never seen this before, the notation is kind of heavy. But the point is that you can actually, for all the points in the domain of the chart, you have this natural bijection. And this bijection is actually linear. If you fix the point Q, this is an isomorphism. So I have this bijection, which is an isomorphism, or which induces so if I call this capital phi, this induces an isomorphism Q dot that goes from Rn to TQM for every Q in U. So now we can use this bijection to topologize the tangent bundle. So you basically say, all the open sets here, the image of all these open sets is going to be an open set in Tm, and you kind of say, take the topology generated by these. I didn't define how you generate the topology, but I think it's not very hard to imagine. So you just kind of glue these tangent spaces all together, kind of using the topology that's induced by the product. So the idea is that, basically, it's a little hard to visualize the tangent bundle, but even for a curve, so say you have a curve. So what is the tangent bundle of the curve? You have every point of the curve, and then at every point you have a tangent space. And the topology on this space is basically given but locally by the product topology. So a different way to visualize this is like, you can think of the curve, and you can think of each tangent space as being kind of transverse to the curve. It doesn't make a lot of sense when I say it's the tangent space, but it's kind of, you're thinking of it like as a product. So it's like each tangent space is like something like this. So for each point, you have a tangent space here. And locally, the topology is the topology of a product. Okay, so this way, you will topologize the tangent bundle. And it's not very hard to see, still using these bijections, that this will inherit the structure of a smooth manifold. So the Tm inherits the structure of a smooth manifold. This is not completely obvious, but kind of clearly here, if you say this defines the topology, you can actually show that this is a topological manifold. This is pretty straightforward. Given a point here, there's a bijection to here. By definition, it's a homeomorphism because you're defining the topology. And of course, given a point in this product, this guy is homeomorphic to a space in Rn. So you have a point in Rn times Rn. So that's your homeomorphism to a point in R2n. So so this is the topological manifold part. And to say that to see that there is an atlas that is smooth, it's a little trickier. But basically you have to see what happens when you change the charts here. So what happens with this bijection when you look at another chart? And it's a little more complicated. There will be transition functions, and there will be the derivative of the transition function is going to appear here. So this is kind of an exercise to see what happens when you go from this product to the product with U tilde. So when you look at this map from R2n to R2n, the transition, the induced map from the transition function, you're going to have the derivative multiplying as a linear map on this part here. So this is very standard, but it's still an important exercise to see that the tangent bundle is actually a smooth manifold of dimension 2n. But it's not any two manifold of dimension 2n. It has this interesting property that you have a linear structure on these fibers. So it's a manifold of dimension 2n, and it has a interesting map, which is called the projection map. So moreover, there is a map which you can think of as a forgetful map that goes from Tm to M, which is often called P. And what it does, it just tells you on which point you are. So if V is in TPM, this map takes V to P. Okay. Moreover, this map is smooth. Okay. So this map will just say take this point here, this vector, and it'll just tell you which point you are over. Okay, so that's the standard projection for the tangent bundle. Okay? All right, so that's the tangent bundle. Any questions about this? Okay, so now let's talk about the cotangent bundle. The cotangent bundle is very similar to the tangent bundle, but it's basically the dual. So now you let TPM star, so this is the cotangent space. This is just, by definition, the dual subspace to the tangent space. So in other words, this is the set of linear maps from TPM to R. And as you know, the dual space to a finite dimensional vector space is isomorphic to the original space. So you might ask, so why do you bother? How is this different from the tangent space? Oh, it's different. There's a bijection. It's isomorphic, but it's different because there is no canonical isomorphism. So you might remember from linear algebra that the dual space is isomorphic to the original space, but not naturally. The dual to the dual is naturally isomorphic to the original space, but not the dual itself. So this space has other structures, which is why it's kind of so important. So it's kind of clear this is a vector space. So this is TP star M is a vector space of dimension n as well. And now a chart induces a basis. You know that given a basis of a space, there is what's called the dual basis of the dual space. So the isomorphism is usually thought with this dual basis. So given a chart, phi, which I'm going to write again, x1 through xn, that goes from u to Rn, to V and Rn. So this induces a dual basis, or this induces a basis that I'm going to call dx1 at P, dxn at P. And what's the defining property of these d blah, blah, blah? The defining property is that dxj at P, when it evaluates at the basis element of the tangent space, this is Kroneker's delta, delta ij, which means it's 1 if I is equal to j, and it's 0 otherwise. So this is 1 if I equals j, and 0 otherwise. Okay? So that's the dual basis. And again, you can play the same game, and you can define the cotangent bundle, which is like this. And this is naturally a 2n-dimensional smooth manifold. And we have a projection as well. So we have a projection from T star of M to M. So this projection is smooth. Okay. So again, you might be like, so why bother? Why is this cotangent bundle? Why are we talking about the tangent and the cotangent bundle? And even though they are very, very similar, they have their intrinsic properties are very different. And I just want to kind of finish the lecture today by showing you how different they are. So one thing that's great about the cotangent bundle is often easier than the tangent bundle. Or not easier, but it has some really good properties. So one of them is the following. So given a function in M, you can actually talk about the derivative of the function at the point P. This is actually a covector. And you actually be able to find this df will actually be a map from M to T star of M for every point in M. And this is actually going to be smooth. And how do you define this? It's actually very simple. So this df, so what is the definition of df of P? So df is just a function. This is just a covector in M. So it's something that's supposed to eat a vector and spit out a number. So what's a vector? Vector is a derivation or a curve, right? So as a derivation, this just will do V times F. V applied to F. And if I write my derivation as the class of a curve, this will just be d dt at t equals 0 of gamma composed with f. Okay, so it's extremely simple. And it's not hard to see that as you vary p smoothly, this thing will vary smoothly, which is why this is a smooth map, df, when you let p vary. So this is called the differential of f. So df is the differential of f. And one very nice exercise is that this notation here is compatible with this notation here. So in other words, the basis for the cotangent space that's induced by the chart, each of these elements is just the differential of the coordinate chart xi. So remember that when I look at a chart, when I write my chart like this, what I mean is that each xi is a function from u to r. So as a function from u to r, it also has a differential. The differential only takes values in u, but it's still a differential. So we have this differential xi at p. And this, by definition, is a function that when you apply this to a vector, this will be the vector, d dt t equals 0 if this is the gamma of gamma composed with the function xi. No, sorry. No, this is the other way around. It's f composed with gamma. Sorry. So this is xi composed with gamma. So it's an exercise to see that this is exactly the same as the dual basis of the basis ddxi. Okay, so I'm gonna leave this as exercise. So the exercise is that the dxi defined this way is indeed the dual basis of the basis for the tangent space. So that this dxi p to the xn p is indeed the dual basis to the basis ddx1 p ddxn p. Okay? All right. So, yeah, are there any questions about the tangent and the cotangent bundles? Oh, I should say one more thing. A map like this is what's called a section. So, I have my, I'll talk about this in more detail later, but I have my bundle, my cotangent bundle. So this induces a natural map that goes from here to here. And the df is a map that goes from M to the tangent bundle. But clearly, if I take a point in M, I go up here, and then I project it back, I go back to the same point for no matter which function. Because the differential of the function is on the cotangent bundle of the point. So when I project it back, I get back to M. This is kind of completely canonical. But if you're not used to it, maybe it's kind of not obvious. But it's extremely canonical. So if you take a point P, then you look at df of P. This is a point in the cotangent fiber at P. So when I use my projection, I project back to P. So this is what's called a section of this bundle. And as you can see here, given any smooth function, you have a very canonical, very easy section of the cotangent bundle. And that's one reason why the cotangent bundle is very nice. I mean, the tangent bundle is very important, but it's much harder to come up with sections of the tangent bundle like this. Like the equivalent thing would be if you have a curve, then you have a bunch of tangent vectors along the curve. But that will only give you a section of the tangent bundle along a curve. Finding a section of the whole tangent bundle is usually much more complicated. It's a lot harder to find canonical sections of the tangent bundle. Okay, I'm gonna maybe say a few more words about that this afternoon. But I think I'm gonna stop the first lecture now. Okay, we'll continue this afternoon at 1 p.m.